Good morning, all. Today we will learn about discrete frequency spectrum and frequency range. Now, first of all, a few definitions. So, let us go through it first. This you all know, frequency spectrum of a signal is a range of frequencies contained by the signal. Then frequency distribution, that is a table of observed values in a sample with the number of times each value was observed. Suppose that you are writing numbers from 1 to 10 and that the digit 1 repeats 5 times. Then the frequency of that number 1 will be 5. So that is the frequency. Now discrete frequency distribution is nothing but a table that lists each number as well as along with that the number of times or frequency that it occurs in a list. For example, suppose that you are taking 3 families and you want to calculate the number of families having one child, then the number of families having two child, like that. So in such cases you use the discrete frequency distribution. That is, a discrete frequency distribution lists all observed values, whereas a continuous frequency distribution lists ranges of values. Okay. Now a discrete frequency domain is a frequency domain that is discrete rather than continuous. Frequency is given by f is equal to 1 by n. Here n is a positive integer smaller than the signal length. So this is the figure for a discrete frequency spectrum. Now, in order to convert a function or signal from time domain to frequency domain or back, that is from frequency domain to time domain, we can use some mathematical operators and they are called by the name transforms. For example, a Fourier transform converts a signal of frequency from time domain to frequency domain, whereas an inverse Fourier transform does just the reverse. That is, it converts a signal of frequency from frequency domain to time domain. Okay. Now, a discrete time signal gave rise to periodic frequency spectrum. In physics and electronics, frequency domain actually refers to the analysis of mathematical functions or signals with respect to frequency rather than time. So, in this session, just study the important definitions that I have underlined. Okay. Now, we learn more about a discrete spectrum. Suppose that you have a periodic signal, that is xpt. P actually stands for periodic, described as a function of time in time domain. Then that particular signal in frequency domain is represented as a sum of frequency components, say from 0 plus or minus f and goes on, where f is equal to 1 by t and this f is known as a fundamental frequency. Now this frequency domain representation of a signal is referred to as its spectrum. So what is a spectrum? You can read from this frequency domain representation of a signal. Now consider a complex Fourier coefficient given by Cn is equal to modulus Cn exponential of j argument Cn. Here modulus Cn represents amplitude of nth harmonic component of the signal. N is the harmonic component of the signal and modulus Cn represents the amplitude of that particular nth harmonic component of the signal. Now the plot of or the graph of modulus of Cn with respect to frequency is called discrete amplitude spectrum of the signal, whereas the plot of argument Cn versus frequency is called discrete phase spectrum. So you can get two definitions. The plot of modulus Cn versus frequency is called discrete amplitude spectrum, whereas the plot of argument Cn versus frequency is called discrete phase spectrum. Okay, these spectra are discrete. Why? Because amplitude and phase possess non-zero values. Okay, so from here, what is a spectrum? What is meant by discrete spectrum? Then which are the two types of spectra, that is discrete amplitude spectra and discrete phase spectrum. Now, discrete frequency spectrum and frequency range. Here, it is said that the frequency response of a discrete system can be obtained by applying a spectrum of input sinusoids to the system. Let us see how it works. The frequency response and at the end gives the gain and phase response. Okay, so before that we'll go through this particular derivation so that the concept will be clear. Suppose that you have a discrete system and let h of n, here it is written, let h of n be the input, be the impulse response. Let x of n be the input given to the discrete system, and let that be a complex exponential of the form e raised to j omega n. Okay, then let yn be the output of the discrete system. So you have a discrete system and hn is the impulse response, input is the xn, and it is of the form of an exponential, complex exponential e raised to j omega n, and let yn be the output. So the output yn of the discrete system is written as the product of impulse response and the input, which is an exponential of the form e raised to j omega n, that is again equal to summation over k minus infinity plus infinity h of k x of n minus k. Now yn, the output is kept is equal to, summation is kept as such, hk is kept as such. Instead of xn, you replace it with the e raised to j omega n. The rest is the same. Here e raised to j omega n is taken out and summation is kept as such. So e raised to j omega n, again it is written as such, and the term involving that exponential part is replaced by the term, or is replaced by the quantity capital H of omega, and that particular quantity is called frequency response of the system. It is given here. Okay, it is called frequency response of the system. So we see that if we force the system with a complex exponential e raised to j omega n, then the output is of the form h of omega e raised to j omega n. In that, e raised to j omega n is the input, and the quantity capital H of omega is called frequency response of the system. Now the frequency, this particular h omega can be written in polar form as this. This is a polar form representation of frequency response h omega. In that you can see modulus of h omega. That particular quantity is called magnitude response. It is discussed in the coming sessions. See, that particular modulus h omega is called magnitude response, whereas the quantity angle of h omega here is called phase response. Okay, now the plot of magnitude response, that is modulus h omega versus omega, is called magnitude response plot, whereas the plot of angle of h omega, angle of h omega is called phase response. That particular the plot of phase response versus omega is called phase response plot. So study these definitions. Modulus of h omega is called magnitude response, angle of h omega is called phase response. So the plot of magnitude response versus versus omega is called magnitude response plot, whereas the plot of phase response versus omega is called phase response. So study the definitions. Now the properties of phase response is listed here. That is, h omega take on values for all omega, that is, it is a continuum in omega, then it is periodic in omega with period 2 pi. The magnitude of the magnitude response is an even function of omega and symmetrical about pi. The phase response is an odd function of omega and antisymmetrical about pi. So just study this for properties of frequency responses. Now the last session, suppose that you have a discrete sequence and its Fourier transform will exist if and only if the sequence satisfies this particular condition, that is sigma as modulus x of n less than infinity, and that Fourier transform is represented by the letter capital of x omega. Okay, so if we have a discrete sequence xn and you are applying or you are taking its Fourier transform, then that sequence xn will be decomposed into its frequency component. In that case, the Fourier transform capital X omega is called by the name signal spectrum. Now Fourier transform of analog signal consists of a spectrum with a frequency range from minus infinity to plus infinity. That's in the case of analog signal, whereas in the case of discrete signals it is unique and it ranges from, that is, the frequency ranges from minus infinity to plus pi. Hence the frequency range for any discrete time signal is limited to minus pi to plus pi, and any frequency outside this interval will have an equivalent frequency within this interval. So just remember this. For analog signals, frequency ranges from minus infinity to plus infinity, whereas for the Fourier transform, the frequency range for discrete time signal is limited to minus pi to plus pi. Okay, so just study the important points, and I am described very well in this session, so go through it. Okay, so that's it for now. Thank you.